Okay, we are now recording. I'll even turn on the projector. And let me go over just a few other sort of the final things. Have you done the student course evaluations yet? Okay, please do those before the end of the term, okay? You can wait as long as you want, but just don't forget to do it. I know when I was an undergrad, end of the term, taking finals, I turned my brain off and went home. I'd forget if I didn't take care of things beforehand. So please don't forget, do the student course evaluation. And that involves some other, you've done them before, so you know. Yeah, okay. All right, that's one. Number two, I've returned all the papers. I'm saying this for this, not for your benefit. Returned all the papers to folks who are here, which is only one, except the research papers. Of course, I have to hang on to those because they periodically ask for samples of student writing. So I have to have those available for about 3 years, and then we have to I toss them. If you want to come back in 3 years, you can get it. Okay. Let's see. And there was a question, and let me go and clarify that. Next week is finals week. So I will be here the same hours I'm here during the regular instructional weeks. It's just I won't be in the classroom necessarily. I do have 2 classes that we'll be taking in-class finals, okay? So let me go over my schedule for next week. Mondays, okay, Mondays and Wednesday classes, all 4 of them are take-home finals. So I won't be in the classroom unless some student comes by to do a test. And then, as I was telling Emmanuel, I'll be somewhere between 265 and 255. What I do is I find the closest classroom that's empty, not being used, to my office, and that's where we do makeup tests. That way I don't have as far to go if I'm going back and forth to my office or the phone rings or something like that. But if all those classes are being occupied, I know this one's going to be empty because I'm the only one that teaches here except Dr. Bryant, and usually I don't have students coming in to do makeup exams for Monday and Wednesday afternoons. But if I do, I'll find 257 is free, so I'll use that. Okay, so Tuesday, I'm giving a final, 8 o'clock in the morning. That'll go 8 to 9:50, and maybe even later, because it's not that long of a final, but that class tends to take a little bit longer to do, and it's a larger class. So I'll be in the classroom at least for those 2 hours, 8 to 10 or approximately, and maybe a little bit longer. Now, Tuesday, I've got a mini-term class. It's Tuesday and Thursday. So actually Tuesday is the last day of class for that class. So we will be having class here that day. That's Tuesday 1:15 to 5:45. However, we probably won't be here the full 4.5 hours, because we'll be, I think, through with material by then. They're going to be, we'll finish the last chapter, do the last chapter's lab, and have the last chapter's test. I don't think that'll take 4.5 hours. It could, but if I'm not in the classroom, I'll be in my office, okay? Then Wednesday, again, don't have any finals, so I'll be in my office most of the day then. And I'll give you my times I'm here. Mondays and Wednesday, 7:45 until 5:15, okay? Tuesday and Thursday, 7:45 until close to 6 o'clock in the evening. 5:45 is when lab technically is over, but usually it takes another 15 minutes or so for me to get everything put away and out. So usually 7:45 to 6. And now, let me talk about Friday. I should have done that first. Normally on Fridays, I have office hours 7:45 to 1 o'clock on the Birmingham West Campus. This Friday, my wife has got professional meetings in Amsterdam, and her flight is out, I think, at 3, so she needs to be to the airport by 1. So I want to take her to the airport because she's coming back on a Friday too, and there's no reason I could pick her up, okay? So there's no reason to put our car and pay for parking for that long. So I'm going to be leaving campus probably around 12:15 at the latest. So I won't be on the Birmingham West Campus as late as 1 o'clock this Friday, because I'll be leaving probably around 12:15. So if you were planning to see me Friday, know that. I'm not going to be there and past 12:15. Okay, then Thursday of next week, my 8 o'clock class would already finish their final unless there's some stragglers, which sometimes there are. And my 9:30 class is a take-home test like y'all do. And then the 1:15 class, I will be meeting with that class. That's the day of their final exam. It's not going to be a long exam, but so I doubt if I'll be in there much past 2 o'clock. So I'll be back in the office. So the class meets here. So now I am giving that class the option of taking it early because some of them live a long way from campus. There's automotive students that come from Mississippi, Florida, all over, and that's their last final. So I'm giving them the option of taking it early if they want to. So that's why I may be giving a test in some other classroom, because I'm guessing most of the automotive students will take theirs a little early so they can get home. Now the other students, the career tech students that are mostly the rest of the class, they may want to wait until Thursday, which is fine, okay, because they have other classes that may be having exams too, and they want to wait until Thursday to do that. So anyway, Thursday, 1:15, I'll probably be in the classroom 1:15 till 2, but if I'm not, check my office or any class in between. And then Friday of next week, same as, 7:45 until 1, okay? My wife's flying back, but it won't be until later in the afternoon, and I can easily get home by 1 o'clock and pick her up. Okay, that's pretty much my schedule. Any questions before we get going on linear algebra? Sorry that took so long. Let's go from current slide. Okay, now I gave Emmanuel the last test. We aren't far enough that all that may not be appropriate, so at the end of the class I'll let you know how many questions to go to. Boy, everything is so slow. I've got the screen, but I don't have a cursor. Bless you. Ah, there it went. Okay. It must have been tired staying up late last night. And I forgot to mark Emmanuel here. I guess I was. Emmanuel's here, and Marcus here. The middle of the alphabet, doing quite well. The top and the bottom, not so well yet. Okay. Now, as I told Emmanuel, I cannot return research papers because they periodically ask for samples of student writing. So that's, I can't return those, but here are your first 2 tests anyway. Now, one person hasn't turned in both of these, so please don't let the answers get out, or else you'll be elevating his grade and diminishing yours. Okay, so lower yours any, but lower relative to the class. There's the test 1. This week we're doing test 2 as well. So find it. There's the part. I don't think you turned in test 3 yet. Need that fairly soon, sooner rather than later. Okay. And also, y'all are doing this on purpose, aren't you? Coming in one at a time. So I have to go through all this 4 times. No, I'm glad to see you. Again, I can't return research papers because periodically they ask for samples of student writing, so I have to hang on to those. But I am returning the first 2 tests. Now, not everybody's turned in the first 2 tests, so please don't let this be seen, because otherwise it will diminish your grade and elevate his grade. Okay? And there's test 2. I don't think I've gotten your test 3 yet, have I? Okay. So get that to me as soon as you can. Oh, and since I did this for Emmanuel, I might as well go and do it for y'all too. Here is your test 4. It says test 3, but it's really test 4. Okay. And we haven't covered everything on there yet, so don't sweat. At the end of the class, I'll tell you how far to go on the test. I didn't know when I was making it out how far we were going to get today, and so far I'm not doing a good job getting anywhere because there's been so many announcements. But I'll say again for y'all because I said it for Emmanuel. Please do the pseudo-course evaluations. If you haven't already, please do those. Please get those done. Don't forget it at the end of the term. Number 2, this Friday, I have to adjust my office hours just a little bit. My wife's flying to Amsterdam and has to be at the airport, has to leave for the airport at 1, so I usually don't get off until 1, so I'm going to be leaving campus, Birmingham West campus, about 12:15. I've worked enough hours this week already to make up 45 minutes, so won't be any problem there. So I will be only have office hours 7:45 until 12:15 or so. Now, if she decides she has to be at the airport at 1, then I may have to leave at 12 rather than 12:15. But we'll work that out. Okay. Now, next week, Emmanuel was asked about where I would be and when. I'm going to be on campus my regular hours. Okay. Mondays and Wednesdays, that's 7:45 until 5:15. Tuesdays and Thursdays, 7:45 until 6. Friday of next week will be 7:45 until 1, as far as I know, on the Birmingham West campus. I say as far as I know. She's flying back on Friday, but I don't think she gets in until later in the afternoon, so I don't think I have to leave early to pick her up at the airport. Okay. That said, I won't be in the classroom my normal times. My Mondays and Wednesday classes, all of them have take-home finals. So Monday and Wednesday of next week, mostly I'll be in the office. I may not always be in the office because I may have students coming in doing makeup tests. Okay, and if that's the case, then I'll be in, not necessarily here. What I usually do is pick a classroom close to my office that's not being used, and I give the test in that office. Okay, that way I can go back and forth to my office with less walking and less time out of the classroom, and also maybe hear the phone ring so I can get to it. I can't hear it up here. So if I'm not in my office, 265, and not in this classroom, 255, look all the rooms in between on this hall. 263, 256, 261, 259, 254, or 257. One of these rooms here will be open. At least this one will be, I know. And if not this one, that one, I know. On Monday, Wednesday afternoons is free. So look for me there if you're looking for me Monday or Wednesday. Now, Tuesday, I do have a final exam, 8 to 9:50. It may actually go longer than that. So early in the morning, come up here, and the test will be here. The rest of the day, then on Tuesday afternoon, from 1:15 until sometime in the afternoon, I'll have class up here. That's a mini-term class, so we have our last day of class next Tuesday. I'm guessing we'll be through before 5:45, but I don't know how long before 5:45. Maybe 3 or 4 or 5 o'clock, but something like that. Wednesday, I already said. Thursday, the 9:30 class has a take-home final like yours, so I'll be in the office. But at 1:15, I'll probably be back here in the classroom because that's when the mini-term class is scheduled for their final. However, I was telling Emmanuel this, I'm giving that class the option because several of the students live out of state even, okay? And if that's their last final, I don't want them to have to hang around till Thursday afternoon to take their last final if they need to get home. So I'm giving them the option of taking their final early. So that's why I may be in some other classroom giving them final anytime during the week. So there may not be anyone here, but the odds are there'll be somebody here taking a final, but it's not going to last long. I'd say if it starts at 1:15, they'll be through by 2, probably, because it's not that bad of a time. All right. Yes, sir. Oh, you need key? Okay. Yeah. Okay. And then on Friday, I'm on the Birmingham campus, 7:45 to 1 o'clock. Okay, any questions on linear algebra? Okay. Please do the student course evaluation. Okay. My memory is we're in Chapter 4, Vector Spaces, 4.1, Vectors in Rn, and page 149, Vectors in Rn. Okay. That's the name of the subsection, and it's the name of the whole section. Okay, so up till now, we've talked about vectors in the plane. That's two-dimensional vectors. Okay? Now we're going to talk about vectors in space, r to the nth. Now that's not r raised to the nth power, that's just the symbology they have for a rectangular coordinate system with n dimensions. Now I can visualize one dimension, that's a straight line, any straight line, one dimension. A plane, two-dimensional, any plane, two-dimensional. The space, three-dimensional. That's as far as my brain will go, okay? But in the rectangular coordinate system, that's all the right angles you can get out of it. But they still call things beyond that r, as if they're rectangular, and it's n dimensions. 4 space, 7 space, 15 space. You just have to visualize that, okay? Not visualize it, imagine it, okay? So, for a vector in space, you would represent by an ordered n-tuple, okay? In other words, this screen, that's supposed to be a parentheses, okay? This thing is not working well today, okay? Okay, let's try this again. Go back. Fantastic. The pen is not working well today. Okay, let's try it again. There we go. Let's just call the variable x, x sub 1, x sub 2, x sub 3, ... all the way to up to x sub n. That would be a vector in space. Throw it if you want to. Okay, good deal. Okay. That's a vector, a typical vector in Rn. I like to call, yeah, and they call it too, in space. Now, again, just like before, that can represent a point in space, and I can't visualize it for you or demonstrate it for you, but on whatever your first axis is, you go x sub 1, the second axis you go x sub 2, third axis x sub 3, fourth axis x sub 4, you go all the way up until you find that point in space. That would be the coordinates of it, or that same notation represents the vector there. You just have to go by whether it's a P or Q, a point on it, or if it's a X or a V or a U or something like that in bold or with an arrow over it indicates it's a vector. Okay? So a point would be something like P equals this. That would indicate that's a point. But if you had X either bold or with an arrow into that, that indicates it's a vector. Okay? That's the only thing you have. Used to be we used angle brackets. This book doesn't. The author does in other books, but not in this book. Okay. And again, we talk about the x sub i's are called the components of the vector or the coordinates of the point. Okay. Two vectors in Rn would be equal if each one. Now, the first they have, if they're both in Rn, they have n components or n. Yeah, if it's a point in coordinates, but two vectors would be equal if each of the components, each one of those n components are equal to each other, just like we did before. The sum of two vectors and the scalar multiples are standard operations just like we had in 2 space and 3 space in n space. So, here's Jonathan. Perfect attendance today. Good to see you. Okay? And before I forget, go on and give to you the last test as well. But I also need the earlier test. Okay. And we may not hit all those. At the end of the class, I'll let you know how far to go on it. Okay. So we're on, in Chapter 4, Vector Spaces, 4.1 Vectors in Rn. And that's the subtitle of the subsection we're in is Vectors in Rn. So here's a definition of vector addition and scalar multiplication in Rn, just like you were supposed. Let the vector u equal to, now this is a vector, you see the symbol there. Of course, that's going to be u1, u2, u3, comma, dot, 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 comma, u sub n. In tuple, in components of that vector. And you have another vector v, and its components would be v1, v2, v3, dot, 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 up to and including v sub n. They both have to have n components if they're in Rn. Okay? So those are both vectors that are in Rn. They're elements in Rn. Now again, that doesn't mean something R is raised to the nth power. That's how you designate what we think of as a rectangular system, though that doesn't really make sense in n space, with n dimensions. Okay, that's what that stands for. Don't think it's a raising something to a power. Okay? And let C be any real number. Okay, any real number, C. Rational, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Any real number. Okay? Then the sum of u and v are defined as this. U plus v is also going to be a vector. It's going to be a vector in Rn, and it will be the vector who's made up of u1 plus v1, comma, u2 plus v2, comma, u3 plus v3, comma, dot, 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 all the way up to comma, un plus vn. Okay? Again, n components of that vector. Each of the components is the sum of the corresponding components of u and v. Okay? Just like you would expect, or I hope you would expect it to be that way. Also a vector. Now, a couple things that means. Vector addition is closed in Rn. If you have two vectors in Rn, the sum of those two vectors is in Rn. The difference is in Rn. We'll not worry about multiplying yet until, well, right now. Scalar multiple by C is defined this way. C times u, vector u, is going to be, and they go on and do it. I thought they were going to string it out, but they don't. CU1, comma, CU2, I see U2, okay, now, CU3, comma, dot, 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 all the way up to CU sub n. Just like you would expect, or I hope you would. It's kind of like you distribute the C across the vector symbol and multiply it by every component in the vector. Okay? Now, as with two space, which we did just a little bit earlier, the negative of a vector minus u would then be minus u1, comma, minus u2, comma, minus u3, comma, 1, 2, dot, 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 comma, minus un. Basically, the C here is a minus 1. You just multiply it by everything. Now, with that definition in mind, now we can talk about differences. If we had u minus v, then you could express that as u plus the negative of v, which is what we do with signed numbers, and you do it with each component, and you basically come up with u1 minus v1, comma, U2 minus V2. You see how dull and monotonous this is, and how very regular it is. That's the good news. Dot, 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 up to and including UN minus VN. Okay, that's vector subtraction. And one other little thing, not worth very much, is the zero vector in Rn is represented by the zero vector. Okay, now the trouble is you have to know that's in Rn, and if that's indeed the zero vector, then every one of those components is zero, and there have to be n components. Okay, the zero vector is defined that way. Not much there, is there? Okay, no component has any value whatsoever. So let's do example 4. Any questions? It's pretty straightforward and hopefully very easy stuff. Okay? All right, let's do example 4. Let U equal -1, 0, 1. I can picture this, -1, 0, 1. That's 3 space. I'll live there. Okay? And VB, vector V, has to be an ordered triplet as well. That's 2, -1, 5. Okay. Find each of the vectors. First, A is going to be U plus V. What's that going to be? One. Is that what you said? I hope so. -1 plus 2, 1. Yeah, okay, got it. Next. Second. -1. Okay, that time that was the correct answer, okay? And what? Okay. Okay, the minus signs are being elusive today, or showing up where they don't belong. I believe that's 1, -1, 6, isn't it? Okay. Let's look at B. It's what? Yeah, I mean, this is so easy. Sorry about that. Okay. As you notice, the first problem is very similar to this. Okay. How about 2U, as in happy birthday? Okay. What would that be? -2, 0, 2. Got it. Okay. How about V minus 2U? Okay. Now, if you want to take several steps to do it, you can. But an easy way to do it is do V minus 2U. So just remember to change the sign of that and go. What would that give you? Okay, I don't think so. Minus 2U. 2 minus a minus 2 is? Say again? 2 minus a minus 2. See, there's your 2U, so negate that. That would be 4. -1. Excellent. And? Ooh. Minus 2U. Second? 3. All right. Maybe we should have taken more steps. Okay. All right. So, that's how we do your basic vector operations. Vector addition, scalar multiplication, and then combinations of vector subtraction and scalar multiplication. Okay? The next theorem looks just like the one we did for R2, except now it's for Rn. Okay? Okay? Properties of vector addition and scalar multiplication in Rn. Okay? Here we have vectors U, V, and now W are all in vectors in Rn.
Are they the same as the three space?
What's that?
Are they the same as 3 space?
Yes. And 2 space. Yeah, they work for any space. Okay? And yeah, if you look back to theorem 4.1, they look identical. 4.1 is in a plane, which is 2 space. And these, can you tell any difference whatsoever? None. So I heard that as a suggestion that maybe I just say, go back and look at ViewTube, okay? You'll see all those are done for plane. They're done here too. So we'll move on. Let's do example 5. And by the way, now y'all have already done your papers. William Rowan Hamilton, considered to be Ireland's most famous mathematician, he did a lot of work with vectors, but if I'm not mistaken, I think way before it was going to be used for this, he developed some techniques in mathematics that were later used in quantum mechanics. Now, I may be wrong on this, because in quantum mechanics we refer to the Hamiltonian. And this is the only Hamilton I know. There may have been another Hamilton that came along and developed that. But see, quantum mechanics didn't show up until the early 1900s, and he died in 1865. So, you know, he must have been way before his time developing some stuff that was true mathematically, but they didn't really have that many applications for it until quantum mechanics came along close to half a century later. Pretty incredible guy. Okay, so let's look at example 5. Here are some vectors. Okay, let's go on and clear that so you won't be confused. Okay. Oh, you may be confused. Okay, here's vector u. 2, -1, 5, 0. What space are we living in this problem? 4 space. 4, 3, 1, -1. Vector w. -6, 2, 0, 3. Okay? These are vectors in R4. They're all vectors in R4. 4 space. Find x using each equation. Here's A. We're looking for some new vector x that wasn't mentioned before, and this is equal to 2u, as in happy birthday, minus v plus 3w. This time, I think I'd suggest that we take it step at a time. So, let's do so. 2 times, just plug in what u is. 2, -1, 5, 0. Make sure I've copied it right, by the way. Minus, now let's do this one. You think you can do that addition there? We'll try. Okay, let's do it. So what do you get? Four minus 3, yeah. Huh? What is it? -14. Got it? Those minus signs are creeping up on us again, okay? Next. Second? 9? Is that what you said? Okay. I don't hear well, okay? 1. Little old 1. Okay. Yeah, 8. Okay. Everybody agree? All right. Now let's do what the operation indicates for the first term, you might say there. What would that be? 4, -2. You say 10? 0, minus, well, let's make it a plus, okay? Is that all right? Okay. What would this be? 14. Minus 9. Second. -1, -8. That right? I just changed that to change the signs of all those and adding. Okay, that makes it maybe, I'm hoping, a little easier. What would this be? Say again? 18. Negative 11. 9. Negative 8. Hi. Okay, let's see what we got. 18, negative 11, 9, negative 8. Got it. Okay. Whew, I think B, we better start over. Okay? So let's do B. We're still finding X. Ooh, no, we're not. Okay. Going to be a little more involved. So let's just erase all this. Now, yeah, these are all simple operations, but they can sure make them a little complicated, can't they? By doing lots of things, not at the same time, but close to the same time. Here's B. Here's what we got. 3 times X plus W is equal to 2U, as in happy birthday, minus V plus W. No, plus X. Shame on me. I wasn't reading. Okay. Okay, did I get it right that time? I think so. How would you solve this or find X? There it is. No, okay. That was a dumb blind joke, by the way. I think I can say that in this room. Okay. Okay. How would you do it? Say again? Okay. Deal with the 3 first. So you tell me what to write. 3 times vector X plus 3 times vector W equal 2 vector U minus vector V plus vector X. Got it? Is that what you meant? Okay. What you would do next? Okay, I like the idea. Subtract the 3W from both sides. Okay. Anything else while we're doing it? Subtract an X from both sides. Now this is what I call chugging and plugging. Okay? Get what you want looking for, then plug in the numbers. I was afraid some of you were going to want to plug in what W was, what U was, what V was, and then mess with all the numbers. Please don't, okay? Chug and plug, not plug and chug, okay? Sometimes it doesn't make any difference here. I think it's far better. Okay, what do we wind up with on the left? 2 times vector X, these add to 0, is equal to 2U as in happy birthday, minus V, these add to 0, minus 3W. We've chugged, let's plug, okay? This will be what? Can we do that without? Can we do 2U? 4. A little louder. Negative 2. 10. 0. I like it. Minus. Say again. 4. 3. 1. Negative 1. Minus 3 times, oh, we were going to do that, weren't we? Okay. Okay, let's do that. Minus. Okay, now, here's the question. Do you want to incorporate the minus at the same time, or do you want to do just the 3 at the same time? Incorporate. So we'll make this a plus then. Maybe I should have done that on the previous one, okay? You want to do that on the previous one? It's up to you. Tell me. Leave it as is or change it to a plus? Change it to a plus, okay? I'm going to change it to a plus. You tell me what else to change. Minus, 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 plus. Yeah, got it. Okay. So what is our minus 3W? $18. Okay. Negative 6. I can do that one, okay. Negative 9. Are you happy with that so far? And you don't have to do it this way. You can do it anyway as long as it's correct. You make mistakes, it's not correct, okay? Okay. So let's see what we got. I like the 4s, don't you? Plus and minus add to 0. So that leaves you 18. Okay, let's see if anything else pans out nicely. They're all minuses, so that would be a little louder. Negative 11, perfect. Okay, then we have 9, and then we have negative 8. Very good. Y'all are clever on this. That was 18. Ooh, where is it? Okay. Shame on me. No, wait a minute. No, okay, never mind. Okay. Where is the answer here? Oh, yeah, okay. Okay, got it. This is 2x. Okay. I see their answer now. Okay? That's 2x, remember? We want to know what x is. So what will x be? Okay, that times 1/2. 1/2 of this, we'll wipe that out. And 1/2 of this, that would be our good old scalar multiplication. What would that be? 9. Negative 11 halves. 9 halves, negative 4. Got it. Okay, because we had a 2x. Got it. Done. All right. Now, the properties of additive identity and additive inverses. Thought we had already done these. I guess we haven't. Not everybody has a book, so let me go on and do those. Let V, okay, now y'all know what we mean. What is the additive identity element in vector addition? The additive identity element. 0 vector, okay, not just 0, 0 vector, okay? And what would be the additive inverse, say, of a vector V? What would be the additive inverse of vector V? We sort of just did it in one of those examples. I've already erased it. Negative V. Because when you add a V to a negative V, what do you wind up with? Say again? One more word. Vector. All right. 0 vector. Okay. Because you add 2 vectors, you get a vector. Okay. So let V be a vector in Rn. Okay. And C be a scalar, really abbreviating like crazy, then the following properties are true. First, this is theorem 4.3, by the way, additive identity is unique. Okay? Guess what it is? It's the 0 vector in that Rn. So that many n zeros in it. So in other words, if you have V plus U, and you know the answer is V, you also know what U is. What is U? What are you? Okay, what is U? It's the 0 vector. I'm sorry. I put the empty set. That's not what I mean. Okay, the 0 vector. With a vector line over it. N zeros there. Okay, very good. The additive inverse of V is unique. Okay? Additive inverse is also unique. And so if V plus U is equal to the 0 vector in Rn, what would U have to be there? Negative V. Okay? Has to be the opposite of V. Okay? Number 3, this one's really hard to grasp. Scalar 0 times vector v is going to be what? 0 vector. Very good. Number 4, also pretty hard to do, is c, any old scalar c times the 0 vector is going to be the 0 vector. C doesn't matter to a 0 vector. And number 5, if CV is known to be the 0 vector, then what has to be the case? Second? Either C is 0, that's a number, or V is the 0 vector. One or the other, we don't know which. It could be both, but only has to be one. And then 6, the last one is pretty straightforward too. If you use the additive inverse of the additive inverse of V, guess what you get? V, exactly. Just think of that as minus times minus is plus. You get V. Pretty straightforward. They do have a proof here. Help yourself with it if you like. There's also a linear algebra applied, pulling a boat out of a lake. Looks pretty interesting to me. Now let's talk about this one other topic, which is a very important one, and this is linear combination of vectors. And we have come so close to doing it, but we haven't actually identified it. An important type of problem in linear algebra involves writing one vector x as a sum of scalar multiples of other vectors, v1, v2, v3, up to vn. Okay? That is for scalars c1, c2, c3, up to cn. Okay? No, that should be the lead-in. So here's what vector x is. This is called a linear combination of this other set of vectors v. c1 times v1 plus c2 times v2 plus c3 times v3 plus dot 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 plus c4 times v4. Okay? Now, I'm sorry. Goodness gracious, I'm trying to go fast and I'm doing dumb things. Cn to Vn. Okay. Y'all were supposed to catch that. Okay, Cn, Vn. Okay. Now, just a moment here. Notice we haven't said anything about what space these are in. This could be anywhere, not necessarily in Rn. This could be R1, R7, R15, or M. It doesn't really matter. Any set of vectors, just because there's n vectors doesn't mean it's in n space. Okay? So don't get the n's crossed up here. I wish they'd have used a different counter here. Certainly all the v's have to be in the same space, and x will be in that same space, but let x is now a linear combination of all those other vectors. That's the definition. All right. Because it's going to take just a little bit of effort, let's do it. Here's an x. Vector x is -1, -2, -2. Okay? Vector u is 0, 1, 4. So far in the same space, which is good. We can't do much if they're not. Vector v is -1, 1, 2. Okay, that's ugly too. Vector w, 3, 3, 1, 2. Okay, I hope that's all. I'm running out of room. These are all in R3, notice. Okay? Now, find the scalars A, B, and C. Those are numbers, such that vector x is equal to AU, that's not Auburn by the way, plus BV plus CW. Okay? How you reckon we're going to do this? In this case, plug them in, plug them in. Okay, plug and chug here. So what will that be? Negative 1, negative 2, negative 2, that's vector x. I did do it right, yep. Is equal to A we don't know, that's what we're looking for, times 0, 1, 4, plus B, which you don't know, negative 1, 1, 2, plus C times 3, 1, 2. Now, how in the world are we going to do that? Yes, you're going to make a matrix ultimately. You're going to do component by component. If you haven't picked up anything else, please remember, anything with vectors, do it component by component by component. So let's do the first component. Negative 1 is equal to, you tell me, negative B plus 3C. Next, negative 2 is equal to A plus B plus C. Okay, that's pretty easy. Next, negative 2 is equal to 4A plus 2B or not, okay, plus 2C. Okay, component by component. First component here, negative 1, is equal to first component here. A times 0 is 0, plus B times minus 1, so that's minus B, plus 3 times C, which is 3C. You see it? Component by component by component. What do you wind up with? A matrix equation, basically, right? Now, do you remember how we did that? Long time passing? Yeah. What would be the easiest way to do that? Gauss-Jordan. Well, at least Gauss. Let's go back. Now, I'm going to do several things at once. Is that okay? All right. First thing, I'm going to basically reverse sides. So I'm not going to do that. I'm just going to tell you I'm going to do it. Okay? Next, I know I'm going to want a 1 in the upper place. This has a 0. So I'm going to flip the first two equations, but write it as a matrix. So this is going to be Gauss-Jordan elimination. So my second row is going to be my first row. That's a legal move, right? So that's going to be 1, 1, 1, negative 2. Do you buy that? Okay? I flipped the first two, so you give me the second row now. 0, negative 1, 3, negative 1. Now, can you see something else to do on the third equation? I'm really lazy. Remember that? Say again? Divide by 2. So what do you get? Remember, we're reversing sides. Remember? 2, 1, 1, minus 1. Yeah, doing them that way. That's all legal, isn't it? In most states, okay? So, what's the next thing we do? Say again? You want 0 for the third? How do we make that happen? Minus 2, row 1, plus row 3. All right, do it. The first row stays the same, 1, 1, 1, negative 2. Second row stays the same, 0, minus 1, 3, minus 1. And the new third row is 0. We know that one. Better be. Next. Negative 1. Negative 1. And what, 3? Okay, I can't hear well. Now, what you want to do next? Okay, 0 under the 1 in the second row. Are you talking about, you want that to become a 0? No, we forgot that. We want it to be a 1. We want the first non-zero entry to be a 1. Okay, been a long time, hasn't it? Okay. Now, we're going to multiply that by -1, but please not yet. I want to add those two first to make a 0 up here. That's going to make it easy. Now, that's cheating, but it's okay. It's all sort of legal. Okay. So let's first do that. Add these two rows together, row 2 plus row 1. Okay. And that produces, what's your new row 1? 1, 0, 4, -3. Now I'm going to negate minus row 2. I'm just going to say it that way. That will become 0, 1, -3, 1. Now, can I cheat again? Okay. Now that I got a 1 here and a -1 there, rather than write it and then write it again, let's just add these two rows together. This row 2 plus that row 3. That'll be our new row 3. Is that all right to do? Is it? Are y'all okay with it? Okay. Yeah. You don't sound too convinced there. Okay. So this will be, okay. I'll let you tell me. 0. Say again? 0. 2. Say again? Say again? -4. Okay. 4. All right. Now, what you reckon we're going to do next? What's that? Okay, what you need the -4 to be a 1, I agree. How do we get that to happen? Divide by -4. Okay. But before we do that, guess what I'm going to do first? That's going to be helpful to add like it is, right? So I'm cheating. I'm skipping steps like crazy. Did you know you could do that? Okay. As long as they're all legal steps. Okay. I'm going to add these two rows. So row 1 plus row 3. That's legal, right? What do you get? That's a new row 1. 1, 0, 0. Say again. Say again. Say again. 1. Okay. All right. Hi. Okay. Now, I can't think of anything to do to the second row, so I'm going to leave it alone. 0, 1, -3, 1. And now we're going to do what you said. Row 3 divided by what? -4. Okay. So that produces 0, 0, 1, -1. Okay. What does that tell you right now? Okay, I got to figure out what it is. That's x3, isn't it? These are our components of the vector x, right? So x3 is equal to -1. Now, to keep from doing, or we could, y'all want to do the last step in Gauss-Jordan or do back substitution? I don't care. Back substitution. So that second equation now says that x sub 2 minus 3 times x sub 3 is equal to 1.
So you don't keep them as A, B, and C?
Oh, you're right. These are not x's. These are c's. You're right. Sorry about that. That's what we're looking for. Okay, we already knew what x1, 2, and 3 were. Sorry about that. This is C. Okay. This, I forgot to erase those. Let me go back and get that. Okay. All right. Where was I? This is B minus 3C is equal to is equal to 1. Okay, but we know what C is. It's negative 1. That would be B plus 3 is equal to 1. So that gives us B is equal to what? Negative 2. Okay, and we know what A is, don't we? A is equal to 1. So it said find A, B, and C. There they are. Whoops, I wrote it in the wrong place. Okay. There's our A, there's our B, there's our C. Okay, yeah, we got them. Let's see if that's what they got. Ah, here we go. A is equal to 1. Okay, B is equal to negative 2. Yes, and C is equal to negative 1. Fantastic. Okay. Ooh, yuck. Boo hiss. We're out of time. That means you have a fairly short final, doesn't it? You can do question 1, and you can do question 2, and you can do, I think you can do question 3. And that's all we can do. Because we haven't talked about polynomial space. We haven't talked about what do you call that? Yeah. We haven't talked about subspaces at all, okay? So let's see, are there any of the rest of these we can do? No, I don't think so. Okay, that's going to be an awful cheap final, isn't it?
It's perfect.
Okay.
Don't say it like that.
Okay. So please, folks, be very careful doing those 3 problems because they're going to count a lot. Okay? So be careful. Take your time, do them right. Sorry we didn't get any further. I should have not run my mouth so much at the beginning.
Everything due, by the way.
What's that?
I said, when is everything due?
Okay, let's go over to that. I didn't mention it before, so let me mention it now. I don't think that, have y'all heard that graduate grades have to be in early by any means? I don't think so. I think they're due like Monday or Tuesday of the week after finals, so I don't think there's going to be an issue there. So therefore, get them to me anytime next week. And again, let me give you my office hours for next week. Mondays and Wednesdays, 8 to 5:15. Tuesdays and Thursdays, 7:45 to 5:15. Tuesdays and 7:45 to 5:15. Tuesdays and Thursdays, 7:45 till 6 o'clock in the evening. And Friday, 7:45 until 1 in the afternoon. Now, please don't wait till 1 in the afternoon to turn in your final, okay? That means I'll be grading all weekend. So, so please get me any tests that are missing sooner rather than later, and get me your final exam, which is going to be really easy, any day next week. You can give it to me this week if you want to. This afternoon, tomorrow, or Friday on the Birmingham campus. All right, good deal.
But I'm going to be giving you all my tests this week.
What's that?
I stopped short on like all of them.
Okay.
But I've been going. I did the problems I could do. I'm going to try to work the problems I can.
Okay.
So I'm going to be giving it to you next week.
Okay.